What are those million points of light in the night sky? So for thousands and millions of years, our ancestors, can you please? Yeah. Yeah. So I will explain everything, okay? I'll explain everything. So, yeah. So millions of points of light in the night sky, people started wondering what are those, and eventually they didn't know what are those. So, but somehow they figured out some patterns in the night sky. So, and in the ice ages, in the ice ages, they have these constellations. They saw the constellations seasonally, and they were able to track the seasons based upon the night sky. They used for to track, wild migrations. So the night sky became a guide for them. And when the ice age ended, they depended upon agriculture. And for agriculture, time tracking was so crucial, right? So they built moon calendars based upon the stars, the solar calendar, the lunar calendars, so that they were able to precisely track the seasons, make used for navigation, a lot of stuff, right? So eventually, over the time, they felt like the night sky is guiding them from above, and they are like very special, the celestial guides, supernatural gods, and they started telling stories about them. A lot of mythologies have come about. So the night sky became part of the human culture, right? Now, around I think 1,000, 2,000 years ago, uh, then they started observing some. There are some star-like objects that they move differently compared to the background stars, right? And they call them planets, means wanderers. Wanderers. So they move differently compared to the background stars. So eventually, with a very careful thinking and observation, they figured that out. There actually we are. Earth is just one planet, and all those are like other planets, right? All those are other planets. All those are other planets belonging to our solar system. Sun is at the center, and all these planets go around the sun. So that's we figured it out. Now, after this, the telescope was invented around 450 years ago, around 400, 500 years ago. The telescope was invented. So once it was invented, we started looking into the night sky, and the night sky presented its wonders. The universe revealed itself, beautiful galaxies, nebula, right, and supernovas, star clusters. The universe is just endless, and we figured that out. All these stars. There are billions of stars that belong to a galaxy called Milky Way, and Milky Way is just one galaxy out of thousands and millions and trillions of galaxies in the universe. Each dot is a galaxy out there. So the universe turned out to be really, really vast, a vast place, right? So the night sky, the universe revealed itself, and there are like more stars in the universe than all the grains of sand on the earth, right? And we are like one sand grain lying in one of the beaches, and all those have planets around it. So one scientist, right, was wondering about the universe, and he was sitting in his garden, and he was thinking about our solar system. He asked a very interesting question: why do planets go around the sun? Back then, nobody knew. So he was the one who, why do planets go around the sun? So he was sitting in the garden in his village, and he saw an apple fall down. Right? He saw an apple fall down. So many of us usually, a normal person, usually we don't care about much. But this guy asked a very crazy question: why did it fall down? Why didn't it go up? He thought like there might be some kind of attraction force of the Earth is pulling us down. So he didn't stop there. Then he imagined a fascinating thing. Okay, if you drop a ball like this, it falls down. But if you throw it like this, then it traces an arc in a parabola. It goes and falls farther. If you throw it a bit fast, even farther. But then he realized, oh my God, actually, Earth is a sphere. So he imagined a cannonball experiment, right? So imagine a cannonball shooter right here. If it shoots a ball, it tries to go in the sideways because it has some velocity, but ultimately it falls down to the earth at tracks. So it is trying to fly away even with a greater speed, a bit farther, even with a greater speed, a bit farther even. So it is trying to fly away, but the Earth is pulling inwards because of gravity. Now he calculated if you shoot a cannonball around at like 8 kilometers per second, he calculated the ball will come back and and hit us in the back. He calculated because Earth is a sphere. That is an orbit he discovered. That's what the orbit is, right? You don't realize that sudden sideways speed, an object neither crashes nor leaves the Earth. It is forever falling around the Earth. That's an orbit he discovered, right? I'll show you a little bit of animation here, right? As you can see here, if you have a cannonball on the Earth, right? So if it shoots, it falls a bit farther. It traces an arc even farther, higher speed, even higher. If you have the right speed, it keeps on going around the Earth, right? It keeps on going around the Earth. Okay?
Sir, how, sir?
Yeah, I'll explain this. It's recording. I'll explain. Yep. So it keeps on going around the Earth. So that object is forever falling around the Earth. Okay? That object is forever falling around the Earth. Now, right? So which is the very reason why the moon is always falling around the Earth, and planet, the sun and all the other Earth and all the other planets going around the sun, because they have certain sideways velocity, but ultimately Earth is pulling. So there is a perfect balance between the outward velocity and the inward pull of gravity, right? So have you ever wondered why? Have you ever wondered, right? Have you ever wondered how satellites are put into the orbit? That's the same way. After Newton discovered, because the satellite is forever going around the Earth, if you observe a satellite launch, the satellite will be placed on top of this payload inside, the rocket shoots up. So after going to a certain distance, it will change its direction towards sideways to make it into an orbit around the Earth, and they reach this particular velocity, right? The 8 kilometers per second, 7.8 kilometers per second. If they reach that velocity, then the satellite will always fall around the Earth, right? That's why if you see an arc like this is a satellite going up and trying to go around the Earth. That's an orbit. This is the genius of Newton. And till today, we use the same equations to put satellites into the orbit and to send to the other planets using Newton's laws of gravity and motion, right? So that is the very reason. So that's how the satellite is an ever falling object around the Earth. Yeah, if you throw a ball at certain speed, let us say 7.8 kilometers per second, the ball will keep traveling around the Earth, right? And if you throw it at greater speed, let us 10 kilometers per second, what happens? The ball will escape the Earth's velocity, Earth's gravity, right? It's all about how fast you are throwing, right? That's one thing, right? So Newton's genius, it worked up. He was able to explain falling apples, the moon going around the Earth, the planets going around the sun. It was beautifully explained. But one thing he didn't understand is that how exactly this gravity works, because there is a lot of empty space between the planets and the sun, as we have seen in the solar system scroll session, right? Solar system scroll session. There is a lot of gap between the planets. Then how exactly the sun pulls all these planets across empty space? What is that mysterious force? How it is working? He himself was very confused. He said, I don't know the cause of gravity. Then that question waited for another 200 years. Then another genius scientist came in. What's that? Einstein. Then Einstein came in and he asked a very interesting question which opened up the cosmos for us. His question was, if gravity is a force, right? then why don't we feel it all the time? Sometimes we don't feel the gravity on the earth. When is that? Tell me. Yeah, what is that? Yeah, when you jump, when you fall down, you will completely feel weightless. Right? Einstein imagined the same thing. So imagine a man falling off a roof, right? Very tall building. As long as he falls, while he is falling, he wouldn't feel any weight. He feels like he's completely floating in this space. Now you imagine, this is Einstein's elevator thought experiment. This is what he thought through, a very genius way of thinking. Imagine, let us say, a 500 floor building, and you are in a closed elevator. You are standing with a cup of coffee on top of the building. Now, if the elevator's cables are suddenly snapped, someone comes in and cuts the cables. What happens? The elevator starts falling downwards towards the ground, right? As long as you fall, while you're falling, you're completely weightless. You feel like the cup before you don't need to hold you and your cup nicely floating in the space before you hit the ground. Everything is falling under gravity. So you don't feel, you are weightless basically. You are weightless when you fall. You don't feel the weight. So you only feel the gravity when you are in contact with something. While you are falling, you don't feel. Which is exactly the same feeling when you get if the elevator is very far in the universe, somewhere in the deep space, it will be freely floating. That exactly same feeling you will get you are in empty space. So you cannot, so Einstein said, so whether you are you will, if you are in a closed elevator, you will not be able to differentiate whether you are falling under gravity on earth or you are in an empty space, floating in empty space. That's the exact same feeling, right? While you are falling, you completely are floating. You understand? Now, let me tell you, that's why, why do you think that is why if the astronauts are feeling weightless, the satellite is an ever falling object around the earth, right? Right? It is ever falling object around the earth, right? And as it falls around the earth, the astronauts feel completely weightless. The astronauts, yeah, the astronauts feel completely weightless, not because they are not in gravity, they are in gravity, but they are freely falling in the gravity, because of which they feel weightlessness. The astronauts in going around the earth in the international space station will feel weightless because they are freely falling under gravity. A very logical way of, genius way of thinking. Now if you see what we are discussed, whether you are if you are in a closed elevator falling on the earth, you may think that you are in space because you are freely falling. You can just nicely, if it's a very, let us say, 10,000 florid building and you are falling, you will not be able to tell any difference. You're freely floating in the space. The same way, you feel that you're excited when the elevator is very far from planets and stars in the empty space. You'll be freely floating. So if you are in a closed elevator here and here, you will not be able to tell the difference whether you are in space or whether you are falling under gravity. The same way, now this is where Einstein gets really genius. So now imagine you are standing on the elevator in the school, in the 5th floor. The earth is pulling you. I can feel my weight. Right? Everything is pulling. If I stand for, like, let us say 4 or 5 hours like this, my back starts paining because my spine is supporting a lot of weight. Even my small hair here, basically it is being pulled towards the ground. Everything, my spine is basically supporting. After 5 or 4 hours or so, my spine will not be able to support. It starts paining. Then I have to sit and lie down. I have to rest my spine. Right? Right? So it is continuously pulling. When you're on Earth, obviously you can feel the gravity. You're being pulled against. Now, if you are in an elevator in an empty space, very far from planets and stars, if you have a rocket attached to it, some boosters, and if you start accelerating upwards, you will be forced against the floor, right? Against the ground, against the floor of the elevator. We cannot try this, but just you will be forced against the floor. And Einstein discovered it is somewhere around 32 feet per second or 9.8 meters per second square or something. If you accelerate at that speed, Newton calculated that's a Earth's gravity called 1g. If you accelerate at 1g in the space, you will feel exactly you are walking on the Earth. You can drink coffee, feel very normal. So Einstein realized gravity and acceleration cannot be distinguished. They both are same. You will not be able to tell the difference between whether you are under gravity or whether you are accelerated through space. The exact same gravity feeling you would get. Then what is gravity? If gravity and motion are the same, gravity may not be a force, right? If gravity feels exactly like motion, then gravity may not be a force. Maybe it is some kind of feature of the space itself. What exactly is it? Then why do Einstein questioned, why do planets go around the sun if it is not a force? Because if it's a force, you have to feel all the time. Then gravity may be a motion. That means these things are following certain paths around the sun. May be a motion. So Einstein imagined this entire space-time is like a fabric, space-time fabric. Now, yeah, heavy objects bend the space-time fabric, creating a curvature. The other planets simply follow that, other objects. Like this, I will show you this little animation here. So this is space-time fabric. A heavy object bend the space-time fabric, right? It creates a curvature, and the other planets, if you take any other planet and roll it, it simply goes around the curvature. That's what Einstein's genius was, right? So it has enough speed, and don't think that this is a 2D bend. It's a three-dimensional, space-time fabric. In all directions, it creates kind of dent, bending in all directions in 3 dimensionals. I've just showed you for one direction, and along that, the curvature, the planets would follow. Because gravity is not a force, right? So there must be something happening in the space. So heavy objects bend the space-time. Heavy objects do not pull on the other objects just because there is no kind of rope there or anything. They bend the space-time. The planets don't move in circles because the sun is pulling them with a rope, but they move the way because the surface itself is curved and the planets follow that curved path. This is Einstein's genius, how he explained the gravity. Right? Now, yeah. Sir, then if follows the curved path because of the space-time fabric, then like showed in the video, then yeah, it is going basically it is going to fall towards the center. You mean to say, right? But as I said, like the planets have enough sideways velocity. The inward curvature and the outward velocity usually matches, perfect balance. So it takes very long period of time for those things, to go into. We are talking about millions and millions and millions of years, right? Usually the outward speed is more, right? And don't think that, that's what I'm saying. Don't think that this is two-dimensional space-time fabric. Think it as a three-dimensional space-time. In all the direction it bends, in all the directions. Right? Heavy objects bend the space-time like this. Now, so matter tells the space-time how to curve, and space-time tells the planets how to move. I'll explain this clearly. Now, because if you see, the Earth also has some kind of mass. It's a heavy object. It bends the space-time, and the Moon follows the path. The same way, so the heavier the object, the deeper the bend, right? The deeper the bend. So this idea inspired one of the great scientists who came after Einstein. His name is Carl Schwarzschild. He was a German physicist. He wanted to calculate how much each object in the space actually bends. Through equations, he calculated. how much exactly that bending is there for planets or stars. Using equations, he was able to predict, right? So it's such a genius. Then he not only predict, he thought something else. He pushed these equations to extreme and realized something inevitable. Heavy objects bend more. Light objects bend bit less compared to the heavy objects. Now, this is a space-time fabric bent by our sun. So he pushed those equations too far and he realized there might be a very, very heavy object in the space that bends the space-time so much not even light can escape. Not even light can escape. How? See, if light cannot escape, would you be able to see it? No. So how do you see objects? For example, you are seeing that wall, means light from that object wall is falling on your eyes. You're seeing that fan because light from that fan is falling on your eyes. If you come in the night, it's completely dark. You will not be able to see anything. But if you turn the light on, obviously the light goes in every direction, gets reflected, and you will be able to see the objects because light from those objects, reaching your eyes, right? Right? So, yeah, everyone, please. Yeah. Please do not make. Right? So, space time, right? Light will not be able to. So, black hole. So, he said there might be a very, very heavy object, right? That it bends space time so much that not even light can escape. So, if light can escape, obviously, you will not be able to see anything there. It's like complete void. So he termed the coin black hole, right? Black hole. But are these black holes real? Where do we find them? And the answer comes from stars. Yes. This is what are stars? Stars are nothing but huge balls of hydrogen gas. Our sun is a star. Sun is also a huge ball of hydrogen gas and helium gas. At the center, if this is the real image of the sun taken by NASA, a huge ball of hydrogen and the gas. At the center, it fuses hydrogen to helium, helium to other elements. So at the center, as it burns that fuel, as it fuses, it creates pressure outside. So it is trying to push all the things outside, but outside layers are trying to fall inside. So there is a perfect balance usually. That's why our sun is in very equilibrium state, very stable state, right? But some stars, the internal pressure becomes very much. It pushes the outer layers outside. The star becomes big and then becomes small. What do we call those stars? Yeah, variables. Very Cepheid variables. Very good. Variable star. But our sun is a very stable state. Now, as the star fuses its hydrogen to helium, helium to other elements, ultimately the last thing that forms at the center is iron. So it cannot fuse that iron into any other element. This is the end, that's the code, very heavy iron. Now, as the star runs out of hydrogen gas, let's take our sun. Our sun runs out of hydrogen gas after like 4.5 billion years. What happens? There will not be enough force from the center to push those layers outside. Then the entire star starts collapsing onto itself. It shrinks in the size, right? But that's how stars die. But how the stars die depends upon their size. A star like our sun, or let us say a star is 8 times or less massive than our sun, then it will become a white dwarf. Our sun's diameter is around 13 lakh kilometers. 13 lakh. At the end of its life, as it runs out of fuel, it shrinks in the size, becomes a white dwarf, which will only be around 10 to 12,000 kilometers in diameter. So, which is almost the size of Earth. So our sun will become the size of our Earth. That's white dwarf. That's our sun. But if the star is around 8 to 20 times the mass of our sun, it shrinks further and further and becomes only 10 to 20 kilometers in radius, in diameter, just 10 to 20 kilometers in diameter, very small, maybe the size of Mount Everest. It will become a neutron star. So dense that even a spoonful of material in the neutron star, yeah, When a spoonful of material, if you take, it will weigh 4 to 5 trillion tons at least. 4 to 5 trillion tons. That's a neutron star, right? Then, if a star is around 20 times the mass of our sun, very big, it collapses in a fraction of a second and explodes, and that entire core will become a black hole, forming a haze around it, which is called event horizon. Not even light can escape that gravity. This will be only 2 kilometers to 5 kilometers in diameter. Imagine a star of 13 lakh, 13 to 20 times means, somewhere around 300 times the size of our sun, becoming just 2 kilometers diameter. Extreme gravity is compressed in a space-time fabric, right? That becomes a black hole. Now, because the massive objects in the universe, right, the sun bends, the neutron star is even heavy mass, it has a very dense object, it bends more, and the black hole, it even bends more. It forms something called a boundary called event horizon. If anything enters this, it's not coming back, right? It's not coming back. And this is called event horizon. That's black hole. But this was predicted by Carl Schwarzschild, right? The black holes were predicted. So, but is it moving? Did you touch? Yeah. Right? So that's black hole. Now, but all these black holes real. Where do we find them? So astronomers, once they found this, they started searching around a constellation called Cygnus. So if they were searching around this, for many years, they searched, and especially one star looked so weird. And as I told you, nearly half of the stars in the night sky, are binary stars, right? I told you. So when they saw this star, especially HD 226868, when they saw this star, it was going around something. So they thought it was a binary star system. Initially, they thought it was a binary star system. But when they looked carefully, they could not see the other star. It was emitting X-rays. It was behaving so weirdly, right? So they will not be able to find it. It was completely void there, which means it's a black hole. Which means it's a black hole. So they found, this was the first ever black hole. Black hole was found, Cygnus X1, and that's HD6868 was the star, and they both in an in a binary system. The first black hole that was found, and it was not only, it was actually Cygnus black hole was eating its companion star, the other star. It was consuming. All the material is falling inside that black hole. Black holes are extremely crazy. They eat the planets, stars, whatever the material that falls into it, it eats, right? That's a black hole for you. And this is one of the, what happens if you go near a black hole. See, because black holes, the gravity is not uniform. The gravity will be higher here, the gravity will be lower as you come away from the black hole, right? So let us say you imagine you are falling in with your feet first into the black hole, an astronaut. And as we are made up of billions and trillions of atoms, your fingertips, the fingertip, whatever the atom that is first there, will be attracted to gravity, because your feet will feel more gravity than your head first. So you will be first stretched like a spaghetti, right? Most of your atoms are like being stretched and stretched and stretched and stretched until your last atom. So each an atom will be stretched apart because of extreme gravity. When all of your atoms will be separated, you will be like a long spaghetti. And ultimately, you have been the black hole. That's how the black hole, the death by a black hole. So if I ever want, if anyone comes and maybe I'm 100 years, I'm about to die. If anyone gives me an option of how you want to die, then I will say maybe the black hole. That'll be a very honorable death. Yeah. Please. No. So now, yeah. So that's not the thing. Yeah. Actually, Einstein's genius was not only that, he predicted something crazy. So the heavy objects not only bend space, but time also he discovered. Gravity bends not only space but time. That's why space time is said, right? So times, please, time slows down near the black hole is said. So let us say, what is your name? Arshad. Harshal or Arshad? Harshal. Yeah. Harshal, and yourself? Harshal, which class are you? Sixth. And who else is eighth class? What class are you? Eighth class. What's your name? Pujyashri. Pujyashri, and yourself? Shresht. Shrestha. Shresht, Pujya and Shresht. Let us say both are, how old are you now? You are both 13. So Shresht and Pujya are both 13 years old now. They both have watches, let's imagine. Now, usually, how our watches tick? Tick, 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 tick. That's how our watches tick. But let's say Shresht goes near the black hole and Pujya stays here. Now, obviously, Pooja's watch on the earth ticks normally, tick, 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 right? But Shrest's watch ticks like this, tick, 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 very slow. Not because his watch is weak or the batteries are weak. That's how space-time works. Gravity slows the time down, and he will be breathing normally, he will be eating normally, everything. No difference for him. But time itself slows down. So one of the craziest discoveries Einstein has made. Time slows down near heavy gravity objects, near gravity. Right? So let's do a simple experiment here. Even actually, this was measured by scientists on the earth also. After Einstein discovered, this was even measured. Now, Pujya is here, Shrestha is here on top of a mountain, Pujya is here on the earth. He's on top of a mountain, both have watches. Scientists actually measured that, as you go higher and higher up, far from the gravity, the watches tick fast. As you closer to the gravity, Pujya's watch, generally, whatever the rate, it's, but if you go, Shrestha's watch will tick faster than Pujya's watch. Scientists have with normal watches, obviously we cannot discover, but you have a very accurate atomic clocks. Scientists discovered that, In fact, many of you, how you know? Yes, boys. Many of you, how you know that GPS satellites, right? As they go around the Earth, very far from the Earth, right? Usually they tick faster. So every time, they adjust the GPS satellites, the timing to match to our watches. You know that? Because those watches tick faster. Because we are closer to the gravity, watch ticks slower. So it's in nanoseconds. They have to adjust every time. Otherwise, the watches will go out of sync. How do you know that all watches are in sync? Because they keep adjusting that. This is real. Time slows down near gravity. Now then here is the experiment. Do a simple experiment. So the sun bends the space-time fabric more, neutron star more, and black hole more. So this is the heaviest gravity. Time even slows dramatically here. The more gravity, the more slow down. Now let's do a simple experiment. Let us say Pujya and Shrestha are here. Both have watches, and Shrestha wants to just travel in a spaceship for an hour near a black hole, and while Pujya stays on the Earth. Right? Now, according to his watch, Shrestha goes in a spaceship for 1 hour. Both are 13-year-olds now. He goes there for 1 hour, travels near the black hole, comes back, and Pujya says, "Why have you been so late? I've been waiting you for 13 years now." And this to him, it's only 13 years on his watch, but she will be 26 years old. Because his watch, his time slowed down by black hole's gravity. So that means Shrestha traveled into Pooja's future, Earth's future. That's time travel.
What about age? Age.
Age, he will be still 13 for only for 1 hour, right? And she'll be 26. And based upon how closer you go, how faster you go, your age, maybe if it's like 2 hours or 3 hours or one day, she'll be maybe might have died long time back. Right? That's time travel. Right? Now, so ratio, but Shrestha feels completely normal. He breathes normally, his heart beats normally. It's not like his heart is beating slow. No, that's a fascinating phenomenon of space time. The gravity slows time. And what is time exactly? That we will discuss in separate session. With the time dilation, lot of light speed. That requires a separate session itself, right? But this is the reality. It's not a science. It's not a science fiction or something. This is the reality, right? Right now. So this was beautifully shown in the movie Interstellar, one of the greatest space movies made. And last year you watched it, right? You watched it. Yeah, you watched it. Many of you, very much in the IMAXs, many of you actually watched it. No, so in the movie, he's a hero, Cooper. Basically, what happens? Earth runs out of resources. All the resources are out, so they will not be able to see any survive on the Earth, right? They are not able to survive on the Earth. Runs out of resources. So for humanities to save humanity, they have to find other planet, right? And astronomers and the scientists, they figured that out. But there is one planet near a black hole called Miller's planet, which has water. So these guys, should go and check to find that planet. They will go in a spaceship. In a spaceship, they will go. They find this Miller's planet, and which is near a black hole, extreme gravity. And in the movie, you could see that the tides are very high when they go near the. How many of you have seen this movie? Right? Imagine when they are in the ocean, how the tides are. That's because of forces from yeah, right. So when they go near the black hole. They go near the black hole, and they find this planet, and they come back. But before leaving, he has a daughter of 10 years. But when he comes back, his daughter will be very old. She gets married, she has children, grandchildren, and she was about to die almost in the end of her life. For him, he will be still like that because gravity slowed his time down. So he didn't age, but on the earth, she aged normally. So it's a beautiful movie. Anyone would love to, watch this movie. That's a time travel, but it's very heartbreaking. But also, that's the harsh reality of the space time. Right now, that's black hole. And now, yeah, black holes. When astronomers, in the end, questions in the end, the astronomers, please, no noise. The astronomers, they were looking at many of what in trying to find what is at the center of the Milky Way galaxy, right? They were trying to find the orbits of the stars at the center, and they found that at the center, many stars are going really fast around something that is invisible. Many stars, extremely heavy something is there. Many stars are going invisibly around something. And eventually they figured out that there is a supermassive black hole at the center of our galaxy, which is called Sagittarius A. Right? Sagittarius A. Now, which is 4.3 million times more massive than the sun. 4.3 million times. Extremely dense. Right? Now, this is the largest black hole that was found, called TUN 618, right? So look at the size of our sun and solar system, very small. The largest black holes can get really, really, big. It's a TUN 618, and this is six. It is as like it is as massive as 64 billion suns. Imagine how massive it would be. Yeah. Yeah. Biggest star? Yeah, star. How many? I don't know the exact the figures, but I think it's almost the same size of Stephenson. It looks like that, right? The black hole is the same size of the largest star, Stephenson. And that is the same, something around 60 billion or 100 billion suns can fit inside Stephenson. Yes? Yeah, boys, please. Please. So that's a black hole. So eventually, astronomers have found, as they were looking into each galaxy, they found that many of the galaxies have supermassive black holes at the center, right? So that's what the black holes are. And by the way, this is the first image of a black hole taken around, I think, 7 years ago. This is the first image of a black hole. It's very far. It's in the MEID 7 galaxy, right? The first, very far. They were able to, take the image of this. As you can see, this is the event horizon. Anything that's going in, not coming out. And one of the fascinating thing is time slows down near heavy objects, right? A lot of gravity. As you go nearby and as you go at the event horizon, you enter the event horizon, time literally stops for you. You'll always be the same age. Time doesn't tick for you at all. Time stops. Right? Cut the call. Cut the call. Image. Right? That's one thing. So that's a bit about the black holes and time travel. Right? I think I'm going to stop it. No, not stay. Okay.